In 2023, the James Webb Space Telescope detected the infrared signature of water vapor around a rocky planet called GJ486b, just 26 light-years from Earth. This world is blisteringly hot, racing around its star in less than 2 days, a place where, by every rule we know, an atmosphere should have vanished long ago, and yet Webb saw water's unmistakable mark. Forcing a single, unsettling question to the surface: is the water coming from the planet itself, or from the star it orbits? If you're drawn to the unknown, subscribe and join the journey as we keep pulling at the universe's loose threads, one mystery at a time. When astronomers first catalogued the faint red dwarf star known as GJ486, it seemed almost forgettable, one of the countless small, cool suns that quietly populate the Milky Way. Red dwarfs burn at lower temperatures, but they endure for unimaginably long spans of time, outliving stars like our Sun by orders of magnitude. From Earth, this one is far too dim to see with the naked eye. Tucked deep in the constellation Virgo, about 26 light-years away. Then, in 2021, something subtle betrayed it. A gentle, rhythmic dimming in the star's light, so regular it looked like a heartbeat, hinted that something was passing in front of it again and again. Careful measurements revealed a planet about 1.5 times the size of Earth, circling its host every 47 days. It's so close that, if you dropped it into our own solar system, its orbit would sit comfortably inside Mercury's path. This compact world is bombarded with nearly 70 times the energy Earth receives from the Sun. Its surface temperature hovers around 430 degrees Celsius, 800 degrees Fahrenheit, hot enough to melt metals. Those numbers alone seem to settle the matter. Researchers assumed they were looking at a dead, airless rock. Under that relentless radiation, any atmosphere should have boiled away eons ago. And there was another problem. Red dwarf stars are notorious for flares and magnetic storms, outbursts that hurl charged particles into space like invisible shrapnel. Over time, those storms can strip gases from a planet's surface the way wind scours sand from stone. By all logic, nothing resembling air should remain on GJ486b. But even hostile worlds can tell stories, sometimes the most interesting ones. GJ486b is classified as a super-Earth, larger and heavier than our planet, but still rocky. That alone made it valuable, almost a natural laboratory for studying how small, solid planets evolve around dim, long-lived stars. With a density of about 7 grams per cubic centimeter, it's probably built from iron and silicate rock, much like Earth, but with a slightly higher share of metal. If you could stand there, if standing there were even possible, gravity would press down about 3 times harder than it does at home. Every step would feel slow, heavy, reluctant, as if you were trying to walk through water that isn't there. Because it sits so close to its star, the planet is almost certainly tidally locked. One hemisphere faces permanent daylight. The other is trapped in eternal night. The day side bakes under a fixed sun, its rocks likely glowing a dull red beneath unending heat. The night side never sees the star at all, and could be hundreds of degrees colder. Between them lies a narrow twilight band, a boundary zone where searing heat and deep cold collide. If even a wisp of atmosphere survived, violent winds could tear from day to night, dragging heat across the surface in a constant, furious exchange. Without an atmosphere, the contrast would be absolute molten stone on one side, frozen silence on the other. Extreme as it is, this world had one feature that made it irresistible to astronomers. It transits. Each time GJ486b passes in front of its star, the system's brightness dips by a measurable amount. And during those brief passages, a tiny fraction of starlight filters through whatever surrounds the planet gas. Vapor, or emptiness itself, split that light into a spectrum, and you can hunt for faint molecular fingerprints. For decades, telescopes like Hubble and Spitzer tried to do this for rocky planets. But they weren't built for signals this small. They could succeed with gas giants, worlds with thick atmospheres that leave bold, obvious signatures, but not with compact stones like this. Webb changed the rules. With its 5-meter mirror and advanced infrared spectrographs, it finally had the precision to probe smaller planets in detail. And no one expected GJ486b to offer anything dramatic. In fact, it was chosen for the opposite reason. It shouldn't have an atmosphere at all. The plan was to use it as a control case, a simple hot rock whose spectrum would be flat and featureless, proving that Webb could measure nothing with incredible accuracy. But nature rarely cooperates with our expectations. Before Webb began observing, teams on Earth studied the red dwarf itself. GJ486 is an M3, Fem-type star, about 1/3 the Sun's radius, glowing orange-red at roughly 300 Kelvin. It rotates slowly, taking over 4 months to complete a single turn, suggesting only moderate magnetic activity. Even so, red dwarfs can be unpredictable. They can erupt with ultraviolet bursts. Their surfaces can be mottled with cool, dark star spots, and that matters, because shifts in starlight can mimic or conceal the chemical traces scientists are trying to find. The first Webb observations came from the Near-Infrared Spectrograph (NPC), collecting light across multiple planetary transits. Each exposure had to be meticulously calibrated, noise removed, detector drift corrected, cosmic ray strikes filtered out, and when the data were finally reduced, the main transit curve looked exactly as it should, a clean, crisp dip. The unmistakable silhouette of GJ486b crossing the stellar disk. Everything was behaving. Then, in the leftover signal, the place astronomers stare when the obvious story is already accounted for, analysts saw a faint but stubborn blemish that refused to go away. A small excess of absorption, centered near 4 microns. The precise infrared wavelength where water vapor leaves its signature. The first instinct was skepticism. The dip was tiny, only a few dozen parts per million, barely peaking above the line where detection becomes faith. A calibration quirk, a statistical fluke, a trick of the instrument, or the star. But months later, when a second transit was processed, the same feature returned, in the same place, with the same quiet insistence. Noise can impersonate meaning once, twice, in perfect alignment. It becomes harder to dismiss. Statistically, the odds of random chance producing that same pattern again were vanishingly small. If it was real, the implication was almost absurd. Water molecules should not survive near a surface this hot. Not here. Not so close to a volatile red dwarf. Not on a planet that ought to have been stripped clean down to bare rock. The result struck at a long-standing assumption that close-in rocky worlds around active stars are atmospheric casualties scoured, sterilized, and silent. Yet something in this system was absorbing light exactly where water does. So the scrutiny intensified. Multiple teams went back to the raw observations and rebuilt the analysis from the ground up. Different pipelines, different correction methods, different ways of modeling the star's behavior. The instruments drift, the subtle fingerprints of systematics, and still. The conclusion converged, the signal persisted. Now the mystery sharpened into a more dangerous question. Where was the water actually coming from? One hypothesis placed it on the planet, not as a thick atmosphere, nothing so generous, but as a thin, constantly replenished veil, sustained by geology rather than stability. Deep inside GJ486b, residual heat and tidal stresses could keep pockets of rock partially molten. In that scenario, steam would seep upward through fissures, venting into space in a continuous, desperate exhale. A world that can't keep an atmosphere, but can bleed one into existence moment by moment. We've seen something like this in our own solar system on Io, Jupiter's volcanic moon, though what Io does with sulfur. This planet would be attempting with water. A second idea was stranger, and in a way more elegant. Water doesn't always need oceans or clouds. Some minerals can lock it away inside crystal lattices, hidden like a secret in stone. Heat those minerals past a certain threshold, and the water escapes as gas, a process known as thermal desorption. On the blazing day side, trapped water could be driven out. On the night side, cooler conditions might allow the surface to reabsorb or redistribute it, creating a thin, transient cycle of release and renewal. Not a stable atmosphere, but a breathing skin. And yet both explanations strain under the same brutal physics. The star's radiation should tear water molecules apart quickly, splitting them into fragments and sweeping them into space. To maintain a detectable signature, the system would need an almost perfect balancing act release matched to destruction, second by second, across a world-sized surface. It isn't impossible, but it is uncomfortably precise, which opened the door to a third possibility, one that moved the source of the water back where the light began. In the cooler regions of a red dwarf's photosphere, water vapor can form naturally, especially inside dark, cooler star spots. If the planet's transit path happened to cross one of those spots, Webb could see the star's own water absorption and mistakenly assign it to the planet. The illusion can be nearly perfect, a planetary transit acting like a scanning beam across the stellar surface, sampling not just starlight, but the chemistry of the star's patchwork skin. Even high-precision instruments can struggle to separate planetary atmosphere from stellar contamination when the signatures overlap. So the investigation couldn't stop at one band. It needed a second lens, a different slice of infrared light. Fortunately, Webb carries another instrument, NISS, that covers a slightly different range. By comparing how the suspected water feature behaves across those wavelengths, astronomers can start to pin down its origin. If the signal strengthens toward shorter wavelengths, it points toward the star and its spotty, water-bearing regions. If it weakens in the way planetary absorption should, the balance tips back toward the planet itself. Those follow-up observations were scheduled soon after the first results landed, because this was no longer just about one overheated super-Earth. It was about capability, proof that Webb can detect molecular features around Earth-size worlds, signals so delicate that, until recently, they belonged more to hopeful proposals than to real data. And once that threshold is crossed, the implications spread outward fast. This single case reignited the debate around red dwarf systems as a whole. These stars make up roughly 70% of the Milky Way. For years, they've been treated with suspicion, too flare-prone, too unpredictable, too likely to tidally lock their planets into extremes. But newer models suggest the story may be more nuanced. If a planet has a strong magnetic field, or if it can constantly resupply gases through volcanism, even close-orbiting super-Earths might cling to thin atmospheres longer than we assumed. If that's true, then the galaxy may be filled with rocky worlds that still carry traces of gas and water despite the odds worlds, hovering on the edge between barren rock and something more dynamic. In the broader arc of planetary science, GJ486b becomes a bridge. It sits between the easy targets, the bloated gas giants with atmospheres that shout their chemistry, and the subtle, terrestrial planets where the presence of air is barely a whisper. Whether the water belongs to the planet or the star, the outcome still refines the methods that will one day be used on cooler, gentler worlds, places where water would not be a contradiction, but a promise. Because science doesn't advance by collecting only the results that fit. It advances when reality breaks the mold. A hint of water where water should not exist forces theorists to reopen old assumptions. Maybe volcanic replenishment can outpace erosion under certain conditions. Maybe red dwarf flares strip atmospheres in ways that depend on magnetic geometry and timing. Maybe our models are right, but incomplete. And so the discovery became what discoveries often become, not an ending, but a beginning. When the observing campaign wrapped, researchers didn't celebrate with certainty. They archived terabytes of data, flagged the anomaly, and started drafting the next questions: more instruments, more wavelengths, more transits, more time. Because somewhere inside that faint absorption at 1.4 micron, whether it came from a planet's last breath or a star's shadowed skin, there was a lesson Webb had just taught us. We are finally sensitive enough to hear the smallest worlds speak. What came next wasn't in the main dip at all. It was in what was left behind. Buried in the residuals was a tiny, stubborn bite taken out of the spectrum, an extra absorption feature centered around 1.4 micron, the exact infrared neighborhood where water vapor leaves its clearest imprint. It was faint, almost embarrassingly so, only a few dozen parts per million, hovering just above the line where a signal stops being a discovery and becomes a statistical mirage. The first instinct was to blame the machinery, an imperfect calibration, a drifting detector, a hidden systematic. But then another transit, recorded months later, was processed from scratch, and the same notch appeared again, in the same place. At that point, coincidence stopped being a comfortable explanation. The odds of random noise reproducing the same feature twice, at the same wavelength, with the same general depth, were vanishingly small. Whatever was happening in the GJ 486 system, something was interacting with starlight in precisely the way water does. That implication was unsettling. On paper, GJ 486b is the kind of world that should have been stripped clean long ago, too close to its star, too hot, too exposed. Water molecules have no business lingering near a surface heated to 430 degrees Celsius, 800 degrees Fahrenheit, under irradiation intense enough to batter most atmospheres into nothing. And yet Webb's data kept pointing back to that familiar chemical signature. Independent teams took turns challenging the result, each with their own pipelines and assumptions. They corrected for stellar variability in different ways, modeled instrument behavior with different approaches, and applied separate methods for removing noise, drift, and cosmic ray contamination. The details varied. The outcome didn't. Again and again, the same absorption feature survived the process. The light itself carried the mark. So the question shifted from, is it real, to where is it coming from? One explanation placed the water on the planet barely, tenuously, in the thinnest breath of an atmosphere. The idea is simple: even a world that loses gas quickly might still leak gas continuously. If the interior remains hot, heated by leftover formation energy, radioactive decay, and tidal flexing, then volcanic outgassing could vent molecules upward in a steady trickle. Radiation would tear those molecules apart and sweep them away. But constant replenishment could keep a wafer-thin layer present at all times. The analogy is often Io, Jupiter's volcanic moon, which continually rebuilds a fragile atmosphere from its own eruptions, though GJ 486b would be doing it under far harsher conditions. A second planetary route is quieter, more chemical than volcanic. Some minerals can lock water into their crystalline structure. Heat can drive that water out as gas in a process known as thermal desorption. On a tidally locked planet, the day side is an oven and the night side is a deep freeze. In theory, the sun-facing hemisphere could continually bake out water from hydrated minerals, while cooler regions might allow the rock to reabsorb trace moisture into lattice sites, creating a slow, cycling exchange between stone and vapor. But both of these planetary scenarios immediately run into the same brutal physics: the star is not gentle. High-energy radiation can split water molecules, and once hydrogen is freed, it becomes a fugitive. At the temperatures implied here, around 700 K in many models, hydrogen atoms can move fast enough to escape gravity outright. Stellar wind then carries them away, leaving oxygen behind to oxidize the surface. For water vapor to remain detectable, the planet would need to replenish it constantly, globally, and with remarkable efficiency, minute by minute, across an entire hemisphere. That need for perfect balance made researchers wary. So a third hypothesis pulled the focus off the planet entirely and back onto the star. Red dwarfs are cool enough, especially in certain regions, to host molecules that would never survive in hotter stellar atmospheres. In particular, star spots can be hundreds of degrees cooler than the surrounding surface. In those cooler patches, water vapor can exist naturally within the star's photosphere. If the planet happens to transit across one of these spots, Webb would measure a spectrum that looks exactly like planetary water absorption. The illusion is so effective that even extremely precise instruments can struggle to separate water above the planet from water on the star. Modeling reinforced how plausible this is. If GJ 486's surface is mottled with spots covering roughly 1% to 10% of the visible disk, simulations can reproduce the observed water-like dip with uncanny accuracy. Under the right geometry, the star alone can manufacture the signal. And yet the planet hypothesis can also be made to fit. A paper-thin atmosphere down at something like 1/10 millionth of Earth's pressure could still alter the spectrum by a few dozen parts per million. Webb's sensitivity has reached the awkward threshold where two very different physical realities can produce nearly identical curves. That is the new problem, not detection, but disentanglement. The most promising way to break the tie is to watch how the feature behaves across other wavelengths. Planetary water absorption typically weakens towards shorter wavelengths, while stellar water features in cool regions can strengthen in that same direction. This is exactly why Webb's second relevant instrument matters, NIRIS, which covers roughly 0.8 to 8 micron. If the 1.4 micron feature changes in the way stellar models predict, it points to spots and photospheric contamination. If it trends the other way, it strengthens the case for a planetary origin. Those follow-up observations were scheduled quickly once the first results settled into robust but ambiguous. In parallel, ground-based telescopes began tracking the star's behavior with obsessive consistency, monitoring brightness fluctuations, searching for rotation-linked variability, and building maps of activity cycles. The logic is straightforward if the spectral dip correlates with star spot patterns and surface activity. The culprit is almost certainly stellar. If the signal remains transit-locked and stable even while the star's visible behavior changes, then the planet's environment becomes the most likely source. Meanwhile, theorists revisited the hard question everyone wanted to avoid. Could any form of water signature survive here at all? Volcanism could help, especially if tidal heating keeps the mantle mobile. Hydrated minerals could contribute, especially if the day-night boundary drives a slow release and recapture cycle. But escape calculations are unforgiving. Without a magnetic shield, charged particles can slam directly into the upper layers of any atmosphere, heating and thinning it. And tidal locking may weaken the dynamo effect needed to maintain a strong magnetic field in the first place. Which is why the star hypothesis remains so attractive. It explains the observation without requiring the planet to perform an almost impossible balancing act. Still, planetary exospheres exist even on worlds we call airless. Mercury maintains a detectable envelope of atoms like sodium and potassium, replenished by solar heating and micrometeorite impacts. Scale that concept up to a heavier super-Earth. Expose it to intense irradiation, and you can imagine a fleeting cloud constantly rebuilt, constantly eroded, capable of imprinting a marginal signature on starlight. Webb's engineers and instrument specialists searched just as hard for mundane explanations. Pointing jitter, detector artifacts, background fluctuations, cosmic ray impacts. None could consistently produce a narrow absorption feature that appears twice at the same wavelength across separate transits. After independent reduction methods, the most stubborn conclusion remained the simplest: the photons arrived already marked. So statisticians did what they could with the uncertainty still standing. Under one set of assumptions, the planetary origin looked slightly less likely. Under another, it looked competitive. One representative breakdown put the probabilities near 45% planetary and 55% stellar, a coin flip weighted by how many spots you assume the star carries, and how aggressively you believe the planet can replenish vapor. In other words, Webb has reached a level of precision where nature can hide two answers inside one signal. That is why the next stage won't rely on a single instrument or a single dataset. Upcoming transits will be observed again and again, with NIRISS to capture the wavelength slope, and with ground-based monitoring to track stellar activity in real time. If the signal rises and falls with the star's mood, the answer will be written on the stellar surface. If it stays pinned to the transit geometry, then even on a world this hot, an atmosphere, however faint, may be clinging to existence. For now, the system remains unresolved, suspended between two explanations that both fit the same delicate dip in the spectrum. But even that uncertainty is a kind of progress. It means the instruments are doing what they were built to do, pulling chemistry out of distances that once felt unreachable. It means rocky worlds are no longer beyond our reach. We're simply entering the era where the questions become sharper than the detections. Somewhere 26 light-years away, GJ486b keeps racing around its star dayside glowing, nightside frozen, while Webb waits for the next transit, ready to catch another thin ribbon of starlight and ask the same haunting question again. Whose water is this? To get that answer, the next phase isn't about bigger headlines, it's about quieter, harder work, pushing Webb's measurements into a regime where even microscopic instabilities matter. Engineers began refining Webb's calibration routines with a single goal in mind: stability at the level of microwave-length precision. At that scale, the observatory behaves less like a rigid machine and more like a living instrument. The faintest thermal breathing in the mirror, minute expansions and contractions as sunlight and shade trade places, can subtly shift the depth of an absorption band. Those shifts are small enough to vanish in most studies. But not in this one, and certainly not in the studies still to come. When Webb turns toward cooler, smaller worlds whose signals will be weaker still, the immediate plan is straightforward in concept and relentless in execution: capture multiple new transits under different stellar conditions. A red dwarf is not a steady lamp. Its surface changes, its spotted regions drift, and its magnetic activity rises and falls. If the suspected water feature strengthens when the star dims, or morphs as star spots rotate into view, then the water likely belongs to the star's own atmosphere. If the feature remains locked to the geometry of the transit, steady, repeatable, indifferent to the star's mood, then the planet becomes the prime suspect. To make that comparison meaningful, new modeling has moved beyond simple spot coverage estimates and into three-dimensional surface mapping. Researchers now build evolving maps of the star's magnetic regions, cool scars, bright faculae, and shifting active belts, and generate synthetic spectra from those reconstructions. The next Webb dataset won't just be inspected, it will be matched directly against these simulated stellar fingerprints to see whether the 4-micron trough can be explained purely by spatial temperature variations across the star's face, or whether it demands genuine absorption associated with the planet. Each improvement adds a new thread to keep from tangling instrument temperature, detector gain, pointing stability, the star's rotation phase, flare likelihood, even subtle baseline shifts from activity that isn't obvious in visible light. The complexity grows almost comically large, but the prize remains brutally simple: a clean yes or no on water beyond our solar system, measured in a way that can stand up to every skeptical reanalysis. Before Webb can do that decisive test, there is a careful step that comes first: cross-instrument consistency. The team's near-term target is to recalibrate the NIRISS detectors so that their measurements agree with Webb's other channels to within 1 part in 10,000. Only then can the telescope run the sequence that matters: most consecutive transits captured across roughly 0 width to sync microns, stitching together a broader spectral portrait. With that full coverage, the suspected band is no longer just a notch at 1.4 micron. It becomes a shape, its shoulders, its slope, its wavelength dependence, and that shape is what can finally tell us whether we are seeing a planet exhaling steam or a red dwarf's cool surface masquerading as an atmosphere. If the planetary interpretation survives, it implies something even more delicate than whether an exosphere, thin enough to resemble the wisps surrounding Mercury. It would not circulate like a familiar sky. It would behave more like a constant leak gas escaping as fast as it is supplied. And yet, even such fragility can be visible. Models show that pressures as low as a few microbars can scatter and absorb infrared light strongly enough for Webb to register, provided the geometry is right and the analysis is clean. The hard question is not detectability, it's supply. Can the world feed that film quickly enough to keep it from being erased? One potential engine is written into the orbit itself. GJ486b's path is not perfectly circular. Its slight ellipticity means the planet is rhythmically stretched and relaxed by gravity as it moves closer and farther from its star. That flexing generates internal friction, and friction becomes tidal heating. The same fundamental process that drives Io's relentless volcanism, but scale it up to a planet 3 times Earth's mass. And the consequences could be far more dramatic. A mantle that stays partially molten for billions of years, magma reservoirs extending deep into the interior, and fractures that can vent material through cracks tens of kilometers wide. If the mantle holds water or hydroxyl compounds, those vents wouldn't release steam alone. They would likely vent a cocktail water vapor mixed with carbon dioxide and sulfur dioxide, rising into a region where it is immediately attacked. Near the substellar point, ultraviolet photons would split water quickly. Hydrogen, light and fast, would escape upward. Heavier fragments would hang on longer, forming a brief, thinning veil that Webb might catch during a transit. In that scenario, the observed signature becomes a balancing act between outgassing rate and escape rate, with the spectrum acting like a live readout of the planet's geologic pulse. But the surface is not a passive stage in this drama. At temperatures above 700 Kelvin, minerals begin to behave differently. Iron oxidizes aggressively. Silicates shed bound water. Sodium and potassium become volatile enough to join the near-surface environment. Each of those processes can inject new species into the exosphere species that carry their own spectral fingerprints, some of which can overlap or interfere with water-related features. So interpreting Webb's data is not just atmospheric modeling. It is also high-temperature mineral chemistry, written in gas and glow. Then there is the night side, an entire hemisphere that may be cold enough for some of those gases to condense. If any vapor migrates across the terminator, it can freeze, settle, and be reincorporated into the crust as hydrates or ices embedded in regolith. Over long periods, this becomes a slow conveyor, volatiles drifting from the hot hemisphere toward the cold one, subtly changing surface composition over time. How efficient that transfer is depends on 2 unknowns that matter enormously: wind speed and atmospheric density. High-resolution circulation models try to fill in that gap. They assume a tidally locked planet with pressures on the order of microbars and simulate how vapor responds under constant stellar heating. Even in a near vacuum, the results can be violent jets racing from day to night, in some cases exceeding the speed of sound, cooling as they cross into darkness, condensing, falling back toward the surface, then re-evaporating when dragged again into the furnace. This isn't weather in the Earth sense. It is a continual redistribution of material at the edge of existence, thin enough to vanish, strong enough to matter spectrally. A separate clue comes from temperature measurements during secondary eclipse. When the planet slips behind the star, Webb can infer the dayside's thermal emission. The data suggest a dayside brightness temperature around 700 Kelvin, consistent with an airless or nearly airless world, yet slightly cooler than a perfect blackbody would predict. That modest difference, just a few percent, could be explained by limited heat transport by trace gas, or by dust lofted by micrometeorite impacts, both of which would subtly change emission behavior without building a true, robust atmosphere. The distinction is small, but in this regime, Small is the whole story. Reflectivity adds another piece. The estimated albedo is below 0, meaning the planet absorbs most of what it receives. A dark, basaltic crust fits that profile well. In the lab, molten basalt, heated to similar temperatures, produces infrared emission curves that closely resemble what Webb sees. If future phase curve observations confirm that match, it would amount to something remarkable: the first remote identification of active lava flows on a rocky exoplanet, on a world with gravity roughly 3 times Earth's. Molten rock behaves differently too. It spreads outward into broad sheets rather than stacking into tall cones, potentially producing flows hundreds of kilometers long across the substellar hemisphere before solidifying. Continual resurfacing would erase older craters, leaving smoother terrain that is constantly refreshed. Over geologic time, heavy elements could sink toward the core, enriching the crust in lighter silicates, another subtle shift that may alter color and emission in ways precise spectra could eventually notice. And hovering over all of this is the star itself, intense, but skewed toward the infrared. Only a fraction of its output sits in the ultraviolet range most responsible for breaking molecules apart. Paradoxically, that can give fragile vapors a slightly longer lease on life until the flare arrives. Red dwarf flares spike UV and particle output on roughly weekly timescales, and each event has the potential to tear away a portion of any exosphere, resetting the balance and reshaping the spectrum. That is why ground-based monitoring is not optional. High-cadence photometers track the star's brightness continuously, flagging outbursts and mapping rotational modulation. If a flare occurs during a transit, it can distort the baseline illumination and create artificial spectral shifts that mimic chemistry. Correcting those effects requires synchronized observations across multiple wavelengths, space, and ground, working together so that what Webb measures can be separated from what the star is doing in the same moment. In the end, the next round of observations is not just a repeat. It is an escalation in precision and context. Webb will return to GJ486b with sharper calibration, broader wavelength coverage, and a star whose changing surface will be mapped rather than assumed. Only then will that faint dip at 1.4 microns stop being an ambiguity and become a verdict, either the signature of a planet trying, against all odds, to keep a trace of vapor, or the quiet molecular shadow of a restless red dwarf wearing water in its own skin. While Webb prepares for those follow-up transits, other eyes are already watching the system from the ground and from orbit, keeping a constant vigil on the star itself. Data from the Las Cumbres Observatory network and the TESS spacecraft are being folded into a living map of the red dwarf's mood. Its brightness changes, its spot cycles, the quiet stretches, the sudden flares. The better we understand the star's temperament in real time, the cleaner Webb's measurements become, and the less room there is for the system to hide behind ambiguity. Beneath that shifting starlight, the planet's interior is still something we can't see directly, but it can be inferred piece by piece from the blunt, honest numbers of mass and density. The best models converge on a world built like a tightened fist, an iron-rich core making up roughly 60% of its total mass, wrapped in a silicate mantle and capped by a relatively thin crust. Deep inside, core temperatures may push beyond 5,000 Kelvin, hot enough that parts of it remain fluid even after billions of years. And if that fluid still circulates, if convection still churns, then a magnetic field becomes possible. But it wouldn't be a familiar field, not like Earth's steady global shield. Tidal locking likely forces the planet to rotate only once per orbit, and that's slow. Constrained spin would change everything about how magnetism is generated and how it's shaped. If a field exists at all, it may be lopsided stronger along the terminator where day and night meet, where temperature gradients and motion still persist, weaker beneath the fixed furnace of the substellar point. That asymmetry matters because charged particles do not move randomly. They follow magnetic lines, And uneven shielding would mean uneven escape gas, leaking away through preferential corridors. Carved, not by wind, but by electromagnetic geometry, one of Webb's long-term ambitions is to catch that pattern indirectly, through subtle shifts in spectral intensity that repeat with orbital phase. Meanwhile, the planet tugs back on its star. That gravitational grip creates a measurable wobble, and radial velocity instruments on Earth continue to sharpen the planet's mass and orbital shape. When those measurements are combined with Webb's transit data, the resulting mean density can be pinned down to within about 5% precision that would have sounded impossible for a rocky world, this small only a decade ago. And with that precision, some formation stories become untenable, while others grow sharper. Planets born around red dwarfs don't necessarily follow the same script as planets born around sun-like stars. The protoplanetary disks are compact, often enriched in heavy elements, and close-in worlds can assemble dense cores quickly before the surrounding gas disperses. In that picture, GJ 486b likely formed from refractory materials, iron, nickel, silicates within the first few million years of the system's life. Any early blanket of hydrogen and helium would have been stripped away fast, leaving behind the bare, metal-rich super-Earth we infer today. So where would water come from in a place like this, if it's present? One plausible route is late delivery, volatile rich impactors migrating inward after the star's most violent youth had calmed. Water delivered in that era might not survive as an ocean or a true atmosphere, but it could persist in quieter forms bound into minerals, locked into the lattice of rock, carried downward and upward again through partial melting over long spans of time. That kind of geological recycling warming, degassing, refreezing, reabsorption could feed a trace vapor layer, thin as a whisper, yet just thick enough to leave its fingerprint in infrared light. To test these ideas, researchers run coupled simulations that treat the planet as a living system across billions of years: thermal evolution, volatile loss, mantle temperature, degassing rates, stellar particle flux. The output is not a single answer, but a narrowing corridor of outcomes when outgassing fades, when crust solidifies, which molecules remain detectable, and for how long. For this world, many models collapse into two broad possibilities. Either a sustained trickle of volcanism keeps producing a short-lived vapor envelope, continually renewed as space strips it away, or the atmosphere died completely long ago, and what Webb sees, if it truly comes from the planet, is only surface-driven, release sublimation, and thermal desorption from minerals that cannot hold onto their water under such heat. Infrared phase curve measurements help lean the argument one way or the other. By tracking how the planet's brightness changes as it moves through its orbit, and especially as it slips behind its star, astronomers can infer how efficiently heat is redistributed. A sharp day-night contrast points toward an airless rock. A smoother decline hints at circulation. Early reads have leaned toward the stark, airless interpretation. But the door has not fully closed. A few percent deviation is still allowed. And in this regime, a few percent is the difference between nothing and something. The next lever is chemistry beyond water. Carbon monoxide, carbon dioxide, and sulfur dioxide each imprint the spectrum at different wavelengths. Detecting any of them would strongly favor active volcanism, because they are classic companions of outgassing rock. The problem is brutal. The expected absorption depths may be under 20 parts per million, right at the edge of what Webb can reliably separate from instrument drift and stellar noise. Confirmation may require stacking dozens of transits, letting weak signals accumulate until they stop looking like chance. That's why this planet is also becoming a test case for collaboration across observatories. Work is already underway to combine Webb's readings with future data from Ariel, the European mission designed to survey exoplanet atmospheres across complementary wavelength ranges. Together, Webb and Ariel can ask a sharper question than either can alone is the one. 4-micron feature an isolated thread of water vapor, or part of a broader tapestry of volcanic gases that reveals an active interior. Time variation could become the most telling signature of all. If the vapor is being supplied by vents, its strength may fluctuate as fissures open, close, or migrate, changes that would be almost impossible to fake with a static stellar spectrum. Detecting that kind of variability would be extraordinary direct evidence of ongoing geological activity beyond our solar system. Another route runs through thermal mapping. Small shifts in infrared emission across successive orbits, tiny, repeatable hotspots, could betray lava lakes or active fissure systems on the day side. Nothing definitive has been confirmed yet, but longer wavelength observations should improve sensitivity to those thermal signatures. There is also the question of tidal heating's fuel supply over very long time scales. Eccentricity should damp out unless something keeps pumping it. An unseen companion planet could do exactly that, maintaining a slight orbital stretch and keeping tidal flexing alive. Radial velocity monitoring continues to search for that companion. Even a body half Earth's mass in a nearby orbit could inject enough gravitational rhythm into the system to keep GJ486b's interior warmer, longer, preserving the possibility of ongoing outgassing. So the picture that's forming is not of a simple dead rock, but of a heavy, metal-rich world enduring constant stress, its surface remodeled by heat and radiation, its near-space environment threaded with transient molecules that do not belong anywhere for long. If vapor exists above it, it is fragile and brief, visible only because Webb is finally sensitive enough to catch what would once have been invisible across tens of trillions of kilometers. And the decisive moment still points forward, toward the NIRIS follow-up, with extended coverage down to 0 with microns. Webb can watch how the feature's slope behaves as wavelength shortens, whether it strengthens the way stellar water does, or weakens the way planetary absorption tends to. Paired with simultaneous monitoring of the star's brightness, that measurement should finally pin the signature to its true source. Until then, the best working picture remains a narrow equilibrium, volcanic release, and surface mineral chemistry, trying to feed an exosphere as quickly as the star erodes it. Every molecule transient, every detection, a snapshot of an ongoing exchange between rock and sky. And soon, with overlapping instruments watching the same transits, every photon will be tracked more tightly than ever before, right into the region where water's absorption begins to taper, and where the system will have far fewer places left to hide. They are chasing a very specific clue now. Not a vague hint of water, but the exact curvature of that dip in the spectrum. If the trough grows shallower as Webb reaches toward shorter wavelengths, it points to vapor wrapped around the planet. If it deepens instead, the water is almost certainly coming from the star's own cooler patches. The entire verdict hangs on a slope so subtle it must be measured to within a few parts per million, an astronomical whisper, balanced on the edge of instrument physics. During each transit, Webb doesn't just take a single spectrum. It builds a densely layered data cube brightness as a function of wavelength, tracked continuously through time. Inside that cube is the transit itself, the clean geometric silhouette of a planet crossing a star, but also the star's own restlessness, tiny shifts in flux, as different regions rotate into view, as spots and faculae distort the surface, as the photosphere subtly changes its temperature pattern. By watching how the 1.4-micron feature behaves minute by minute while the planet moves across different chords of the stellar disk, astronomers can, in effect, reconstruct a crude two-dimensional temperature map of the star. If the feature stays steady from ingress to egress, that steadiness favors a planetary source. If it fluctuates with the planet's path, strengthening as it crosses a cooler patch, weakening as it crosses a warmer one, then the star has betrayed itself. That's why the follow-up plan is deliberately synchronized. While Webb works in infrared, ground-based telescopes will watch the same transits in visible light, where star spots reveal themselves more bluntly. A spot that looks subtle in the infrared can appear as a clear optical dimming, So if a change in the infrared water signal lines up with an optical dip at the same moment, the case swings towards stellar contamination. Coordinated campaigns from Chile, Spain, and Hawaii are timed to cover these narrow windows, so that each spectral frame from Webb can be paired with a matching measurement of the star's brightness and color taken at that exact instant. To make that comparison meaningful, the calibration has to be ruthless. Even a small mismatch between instruments between NIRSPEC and NIRIS, or between two ground observatories with slightly different filters, can bend the measured slope of the absorption line. Engineers at the Space Telescope Science Institute have been tightening the calibration chain, improving flat field corrections, tracking detector gain stability, and holding temperature stability to within thousandths of a degree. Webb's mirrors breathe thermally, tiny expansions and contractions that nudge focus and subtly alter the apparent depth of narrow spectral features. So the observing sequences include periodic adjustments and extended baselines, lasting hours before and after each transit, to measure the star's own variability when the planet is not in front of it. That out-of-transit spectrum becomes the reference. Subtract it carefully, and what remains should be tied to the crossing itself. At the same time, other ground facilities are probing the star's magnetic architecture directly. Polarimetric campaigns with instruments such as CFHT and high-precision radial velocity programs like HARPS can infer the topology of surface magnetic fields. Those magnetic maps correlate strongly with where cool spots form and how large they are. Feed that into radiative transfer calculations. Generate synthetic spotted star spectra at different rotation phases, and you get something powerful. A forward model of what the star alone should look like in Webb's wavelength range. If those synthetic spectra reproduce the 1.4-micron dip without invoking any planetary vapor at all, the star can carry the blame. Rotation helps, too, because it offers a slow clock against the planet's rapid one. The star turns roughly once every 4 months, while the planet transits every 1.47 days. That means each transit samples a slightly different stellar longitude. Over weeks, Webb effectively scans the star strip by strip, building a time series that can be tested for periodicity. If the feature waxes and wanes in step with the star's rotation phase, it behaves like a spot-driven imprint. If it refuses to follow the stellar cycle, remaining stubbornly constant across changing longitudes, then the planet's environment becomes the more plausible origin. Flares are the other trapdoor. Red dwarfs can spike suddenly, and those bursts can contaminate spectra in ways that mimic molecular absorption. A flare during transit could inject transient features or shift the baseline illumination enough to fake a deeper trough. That's why TESS monitoring continues, joined by radio observatories that can flag magnetic outbursts. Real-time alerts allow analysts to tag and exclude flare-affected segments before combining exposures, because once you stack corrupted data, the error becomes convincing. Under the hood, the entire disentangling effort becomes a statistical duel. One model represents stellar contamination spot coverage, spot temperatures, facular contrast, rotation phase, flare likelihood, noise terms. The other represents a planetary atmosphere or exosphere scale height, molecular abundance, temperature structure, day-night transport efficiency, and its own noise terms. Bayesian inference turns those into probabilities rather than opinions. Using Markov chain sampling, computers generate millions of synthetic spectra, compare them to the real data, and keep updating the odds with every iteration. The winner is not the most exciting story, but the one that leaves the smallest, most patternless residuals across all wavelengths at once. Early trial fits with existing data leans slightly toward the star, just barely because spot models can shave down the residuals by a hair. But that advantage is still trapped inside calibration uncertainty, which means the current evidence is suggestive, not decisive. The NIRIS measurements are the lever that should break the tie. And this matters far beyond a single planet. Red dwarfs dominate the Milky Way, and their surfaces are far more chemically and magnetically textured than the Sun's. Star spots and faculae can alter apparent transit depths at exactly the scale fractions of a percent, down into the parts per million regime, where we expect the faint signatures of Earth-sized atmospheres to live. If astronomers can't model and remove these stellar effects correctly, even the best telescope will sometimes discover air that belongs to the star. That's why this system is quietly becoming a calibration benchmark for the field. Laboratory work on Earth is tightening the molecular foundations. Furnaces recreate the temperature and pressure conditions of cool stellar layers, while precision gas cells provide reference water vapor absorption lines. Matching those references to Webb's measurements refines the molecular line lists that retrieval codes depend on. The better those line lists become, the less room there is for false atmospheres to masquerade as planetary truth. There's also a cleaner geometric trick: secondary eclipse. When the planet slips behind the star, Webb briefly receives pure starlight planet removed from the scene. Compare that to the combined light measured just before eclipse, and the planet's emission can be isolated. If the water feature persists even when the planet is hidden, it must be stellar. If it vanishes during eclipse and returns during transit, the planet has left its fingerprint in unmistakable timing. But that experiment demands exquisite stability and timing accuracy within seconds. Across orbits separated by days, Webb's schedule is therefore optimized for thermal equilibrium sunshield illumination, kept as constant as possible, because even slight temperature changes in the observatory can imitate the very spectral changes they're trying to measure. If the shorter wavelength slope confirms a planetary signal, the next phase becomes quantification. Retrieval algorithms will translate absorption depth into scale height and effective thickness of gas. With the dayside temperature and a water-dominated composition, the implied pressures would be extraordinarily low, far below Earth's an exosphere more than an atmosphere, where molecules rarely collide and the boundary between air and space becomes a blur. Detecting a signal there would be a demonstration of Webb's reach as much as a statement about the planet. If, instead, the slope strengthens toward shorter wavelengths and the star is responsible, the result is no less valuable. It would represent a direct measurement of water in a red dwarf photosphere, placing new constraints on convection, magnetic mixing, and molecular opacity in cool stars, areas where stellar models still struggle. Either way, the mystery does not evaporate. It transforms, and in that transformation, it teaches the field how to listen more carefully. Finally, there is one more subtle discriminator waiting in the data itself: the shape of the line. Planetary absorption, broadened by bulk motion and thermal structure in a surrounding gas, tends to be symmetric. Stellar lines, sculpted by turbulence, magnetic splitting, and complex surface dynamics, can skew. By comparing the suspected water band's line profile to nearby atomic features with well-known stellar behavior, analysts may find the faint asymmetry that gives the game away one last delicate fingerprint hidden inside the trough. Pulling that last clue out of the spectrum means going beyond. Is the dip there, and into what shape does the dip really have? The asymmetry, if it exists, is a second-order fingerprint, so faint that it only becomes visible when the data quality climbs into extreme territory. In practice, that means pushing the signal-to-noise ratio past 1.000, a brutal standard for an Earth-scale world, but not out of reach once enough transits have been stacked and the instrument behavior is pinned down with surgical precision. And that's where the workflow begins to look less like traditional astronomy and more like pattern recognition at the limits of physics. After combining multiple transits into a single high-fidelity spectrum, teams are now deploying machine learning classifiers trained on vast libraries of simulated observations. These networks don't just look for one line at 1.4 microns, they learn the relationships across many wavelength bands, how water-like absorption should co-vary with neighboring features if it comes from a stellar spot, versus how it should behave if it's being imprinted by a thin planetary envelope. Once those models are validated, they can sift through new datasets in hours instead of weeks, turning what used to be slow, artisanal analysis into something that scales. What's being built here won't stay local to this one target. The aerial mission, designed specifically for atmospheric time series work across hundreds of exoplanets, will inherit the playbook: almost intact multi-wavelength slope tests, simultaneous optical monitoring, and star surface reconstruction as routine steps rather than special case interventions. And beyond that, the planned Habitable Worlds Observatory will push the same logic into a different regime: direct imaging, where composition is read not from transit-filtered starlight, but from reflected light peeled away from the star's glare. The methods will evolve, but the core lesson stays the same. You can't interpret a planet until you've learned to subtract its star correctly. Back in the present, the statistical picture is tightening transit by transit. Each additional observation doesn't simply add data, it reshapes a cumulative likelihood curve that weighs the planetary and stellar hypotheses against each other. One probability line will rise slowly, the other will sink, and eventually the gap will become too wide to argue with. Many teams expect the separation to become decisive after roughly 50 hours of total observing time, an amount that becomes feasible within Webb's extended operational horizon, provided scheduling and stellar conditions cooperate. The broader meaning is hard to miss. This is the frontier problem: how to untangle stacked layers of information carried by the same photons. In this one narrow spectral notch, you may be seeing signals written in 3 different places at once: within the star's convective skin, within the planet's near-surface gas, and even in the intervening space the light has crossed. Learning how to separate those layers isn't just a technical exercise. It's the difference between confidently identifying life-related molecules someday and chasing mirages for decades. So the preparation continues with the quiet intensity of a launch countdown. Operators rehearse pointing sequences. Engineers watch detector temperatures and refine calibration routines to tame micro-variations that can masquerade as chemistry. Software teams update retrieval codes with improved molecular constants and better stellar contamination priors. When the next window opens, Webb will settle onto the system again and hold it for nearly 10 continuous hours, collecting spectra with the patience only a machine can sustain. Every photon that arrives will carry a tiny history of its encounters, scattered, absorbed, re-emitted, filtered through matter, and that history is what the analysis must decode. In the end, the verdict won't come from any single plot. It will come from agreement convergence across instruments and techniques. The Nyris slope must tell the same story as the optical light curves. The phase curve thermal behavior must be consistent with the presence or absence of gas-driven heat transport. Only when those independent threads weave into a single narrative will astronomers say, with confidence, whether the water signal belongs to a planet breathing faintly above molten rock, or to the cool scars of a red dwarf's surface. But even before that final synthesis arrives, the campaign has already rewritten the rules for studying small worlds. Infrared spectroscopy of rocky exoplanets used to be mostly theoretical, a promise waiting on better sensitivity. Instruments were designed with gas giants in mind: bloated atmospheres, huge signals, forgiving targets. Pulling a molecular signature from a planet barely 3 times Earth's radius forces a different standard of precision, and that hard-earned experience becomes a template for everything that follows. That matters because rocky planets around red dwarfs dominate the nearby census of possible Earth analogues. Their stars are small and dim, so the habitable region sits close in, meaning more frequent transits, shorter orbital periods, and faster accumulation of data. The same geometry, though, exposes those planets to harsh radiation and magnetic volatility. This system becomes a stress test for the idea that atmospheres and, by extension, surface water can persist under such conditions. If an 800 degrees Fahrenheit world can hold even a transient veil of vapor, then cooler planets in similar environments might have far more resilience than older models allowed. At the heart of that resilience is a simple contest: gravity trying to hold gas down, and stellar energy trying to tear it away. Ultraviolet photons split molecules high in the atmosphere. Hydrogen escapes easily, and over geologic time the sky can be stripped clean. Where exactly the balance tips where a rocky planet crosses the atmospheric survival line has been one of the most uncertain boundaries in planetary science. Now, this dataset begins to pin it down. It shows whether mass and composition can compensate for stellar violence, or whether close-in rocky worlds are doomed to become bare, glowing stone. And it changes something else. 2. How astronomers interpret silence. A flat spectrum once treated as evidence for clouds or no atmosphere at all can no longer be read so simply. Sometimes featureless is not emptiness, but interference. Stars are not static bulbs. They are dynamic, structured, molecularly complex surfaces, capable of writing their own false signatures into the light we measure. Accounting for that complexity won't just sharpen this one mystery, it will recalibrate the entire search for atmospheres on Earth-sized worlds. And that is exactly why red dwarfs have moved from common background stars to center stage in exoplanet science. They're not a niche population, they're the majority, making up roughly 70% of the Milky Way's stars. And yet, for all their abundance, we're still learning how to read them properly. Their photospheres sit in an awkward temperature regime, hovering near the point where molecules can survive. Water vapor, carbon monoxide, even titanium oxide can all leave fingerprints in the same spectral neighborhoods, stacking and blending until the signal becomes a knot of overlapping features. On Earth, we can measure molecular absorption in laboratories with extraordinary care, but those lab spectra rarely capture the brutal realities of a stellar surface. High pressures, intense magnetic fields, and the constant churn of convection shaping what those lines actually look like. That's what makes Webb's measurements so valuable even before the mystery is solved. They are not just data about a planet. They are a reference point for an entire class of stars whose detailed spectra remain imperfectly modeled. A benchmark. Finally, anchored to real observations in the environment where our theories most often slip. At the same time, the planet itself is forcing a rethink on the geological side. A super-Earth 3 times our mass. Denser, heavier doesn't cool like a smaller world. It holds on to primordial heat longer. Pressure, deep in the interior, can keep portions of the mantle partially molten for billions of years, even when the surface has long since hardened into a crust. In that scenario, volcanism doesn't have to be a brief, youthful phase. It can be an ongoing pulse, quiet, persistent, and stubborn, capable of feeding the space just above the planet with intermittent plumes of water vapor, carbon dioxide, and sulfur-bearing gases. If similar signatures turn up on other scorched super-Earths, it would point toward a broader pattern, not dead cinders, but worlds with restless interiors, rebuilding thin atmospheres again and again as stellar winds tear them away. The secondary eclipse measurements have already tightened the leash on what's possible. The dayside temperature hovering near 865 degrees Fahrenheit lands almost exactly where a bare, sun-blasted rock should sit under direct illumination. That single constraint is powerful. It pushes any putative atmosphere into the realm of the extremely thin, less than 1% of Earth's pressure, if gas exists at all. It can't behave like weather in the familiar sense. It would be a tenuous skin, likely short-lived on human timescales. And yet, if a signal is genuinely present, replenished often enough to keep reappearing, that balance is where the physics becomes both harsh and strangely elegant. Geophysicists can estimate how much degassing would be required to offset the losses driven by radiation and stellar wind. And the numbers are dramatic, perhaps 10 to 100 times Earth's current volcanic flux. Extreme. Yes, but not impossible, for a massive planet with a hot interior and sustained tidal stress. In that picture, the atmosphere isn't stable, and it isn't gone. It's a moving equilibrium, an endless exchange between rock and space, supply and erosion. renewal and escape. For astrobiology, this matters even if the world itself is obviously too hot for life as we know it. A thin atmosphere still rewrites surface chemistry. Ultraviolet light can split water molecules apart, leaving oxygen atoms free to attack minerals, oxidize the crust, and subtly change how the planet reflects and emits radiation. Those alterations can show up remotely: tiny shifts in albedo, small changes in infrared glow, offering indirect evidence of active geology on planets where no lander could ever survive. In a sense, the chemistry becomes the planet's handwriting, not a sign of habitability, but a sign of internal motion. From the observational side, the system is also a brutal demonstration of how small the signals really are. The transit itself dims the star by less than 0.01%, and the molecular features ride on top of that as mere tens of parts per million. Extracting meaning at that scale demands near-perfect discipline, removing instrumental noise, pointing jitter, cosmic ray hits, thermal drift, every tiny bias that can masquerade as a molecule. The correction strategies sharpened here, decorrelating spectral channels against spacecraft temperature, stripping out time-dependent detector bias. Mapping subtle systematics won't stay confined to this project. They'll be folded into the standard pipelines of the next decade. And that timing is not an accident. A new generation of observatories is arriving. The extremely large telescope in Chile will soon begin hunting and characterizing rocky worlds from the ground. And NASA's Roman Space Telescope will expand the census of planets and their host stars. But both depend on the same vulnerability: stellar variability. If we don't understand how star spots and magnetic regions distort spectra, direct imaging campaigns risk mistaking the star's own chemistry for the planet's. In that sense, this nearby system, just 26 light-years away, becomes more than a curiosity. It becomes a calibration manual the field can't afford to ignore. The implications reach even deeper, back into the story of how rocky planets are built. If water can appear, however briefly, around a world this hot, it suggests volatiles may survive far deeper inside terrestrial planets than some models assumed. Water doesn't have to sit on the surface to be present. It can be locked into silicate minerals, bound as hydroxyl groups, or even stored as hydrogen in iron-rich phases within a mantle. Over time, as a planet differentiates and its interior circulates, that hidden inventory can be released through volcanism. Knowing how much water remains bound versus how much is lost reshapes our estimates of the original water budgets of rocky worlds, including the one we live on. It also forces a quiet recalibration of what we mean when we talk about a habitable zone. Traditionally, it's defined by temperature, where liquid water could exist on the surface. But the more we learn, the more retention becomes just as important as warmth. A perfectly temperate orbit means nothing if a red dwarf strips away the atmosphere faster than a planet can replace it. That realization pushes the inner edge of habitability outward and may narrow the number of truly viable worlds around M-type stars. The observations here offer something rare in that debate: an empirical anchor, rather than pure theory. Inside the archives, the work continues in the way modern astrophysics almost always does, through layered verification, rather than a single triumphant moment. One team fits parametric models to tame stellar noise. Another uses machine learning retrievals trained on synthetic spectra. Others focus on instrument systematics. When independent approaches converge, confidence hardens. When they don't, the disagreement becomes its own clue, pointing toward missing opacities in molecular databases, underestimated detector drift, or an incorrect assumption about spot coverage. And even if the final verdict declares the water signature stellar rather than planetary, the result isn't a disappointment, it's a resolution with consequences. It would confirm that red dwarfs can host cool, molecule-rich regions on their surfaces, small chemical laboratories shaped by magnetism. If star spots cover enough of the photosphere, they don't just alter the light we measure, they alter the spectrum bathing nearby planets, changing the photochemistry those planets experience. Future habitability models around M-dwarfs will have to treat that effect as part of the climate system itself. That's why engineers are already adjusting designs for Webb's successors, adding redundant temperature sensors to track subtle drift, refining calibration sources to cover the exact bands where red dwarf molecules absorb, building instruments that are less ambiguous from the outset. The payoff is cumulative. Each difficult case reduces uncertainty for the next. Behind it all is a collaboration spread across continents, more than 24 institutions, each holding a different piece of the puzzle. Analysts in Arizona comparing notes with modelers in Geneva, hardware specialists at Goddard checking assumptions against detector behavior, stellar magnetism experts cross-validating with atmospheric retrieval teams. Often, progress arrives through mismatch, a predicted line depth that won't match the observation, a simulated spectrum that fails in one narrow window, a residual that refuses to vanish. Those frictions don't slow the work, they guide it. And somewhere beneath all of the technical detail, there's a quieter impact that's harder to measure but just as real. Every time a faint absorption line is confirmed or ruled out, our mental map of the neighborhood sharpens. 26 light-years away stops feeling abstract when its photons arrive carrying chemical information we can argue over. The discovery doesn't change daily life, but it does change perspective. It reminds us that atmospheres are not guaranteed. Worlds can lose them, worlds can rebuild them, and under slightly different circumstances. Even Earth's sky, so familiar we barely notice it, could have been something far more fragile. Watching that struggle play out around another star gives us something we rarely get in science perspective. It turns Earth from a default setting into a data point. Our own atmosphere, this thin, breathable skin, exists only because gravity holds it. The sun doesn't strip it too quickly, and life has learned how to reshape it without destroying the balance. When we see a rocky world on the edge, flirting with loss, we begin to understand how narrow that window really is. That is why funding agencies are paying attention, not just because the story is dramatic, but because the stakes are practical. If Webb can pull molecular fingerprints out of the light of a rocky planet, it validates an entire future of billion-dollar observatories built specifically for atmospheric work. And if the verdict ends up pointing to stellar contamination, if the star's own chemistry can masquerade as a planet's, then that is not a dead end. It's a signpost. It tells the community where the limits truly are, and where new tools must take over ultra-high-resolution spectroscopy from the ground, coordinated multi-band monitoring, and ultimately direct imaging that separates planet light from starlight altogether. Either outcome speeds the field forward by removing guesswork about what to build next. For students stepping into astronomy now, this system will become a first lesson in how discovery actually happens, not as clean answers delivered on schedule, but as evidence that refuses to behave. Ambiguity isn't failure, it's the pressure that improves the instruments, sharpens the models, and forces another round of observing. That loop measurement, doubt, refinement is the engine of empirical science. A signal that might be water is more valuable than silence, because it makes everyone better at hearing. Meanwhile, theorists are using the constraints to explore chemistry that feels almost unreal. At 800 degrees Fahrenheit, silicates can begin to shed material into the gas above them. Sodium and iron can appear as vapor phase actors, and even a trace amount of water becomes chemically consequential, reacting to form exotic hydroxides that no Earth atmosphere would normally host. Those reactions matter because they change opacity, how efficiently heat escapes, which in turn changes what the planet looks like in infrared. Including that high-temperature chemistry isn't decorative detail. It's how models become honest about superheated rocky worlds across the galaxy. Geophysicists are also digging into the planet's tidal locking for hints about what its interior might be doing. A world split between permanent day and permanent night isn't just a climate oddity, it's a mechanical one. The sharp thermal gradient concentrates stress along the terminator, the thin twilight seam between blistering rock and cold darkness. Simulations suggest that such a planet might develop convection patterns unlike anything on Earth. possibly funneling volcanism into a continuous ring rather than scattered hotspots. If that's true, gas wouldn't need to seep everywhere to be detectable. It could rise preferentially from that boundary zone, steady plumes instead of global eruptions, and future phase curve observations could hunt for that signature as localized infrared hotspots. Even the star's own chemistry becomes newly important. If the water band is stellar, it implies cool surface regions where molecules can persist, and that carries consequences for how we model mixing. Magnetism and the distribution of oxygen and hydrogen in the outer layers of red dwarfs. Those details ripple outward. Red dwarfs dominate stellar populations. They also dominate the light of many distant galaxies. Better models of molecular opacities in these stars don't just improve exoplanet work, they improve cosmic interpretation at scale. So, whichever way the argument breaks, planetary vapor or stellar mimicry, the outcome feeds back into our understanding of worlds, stars, and the messy interface between them. Each observation adds another entry to the growing catalogue of planetary environments: thick hydrogen blankets, bare metallic rocks, tenuous ghost atmospheres, and cases like this one that sit on the boundary and refuse to declare themselves. Together they form a continuum, and that continuum is what tells us where Earth belongs. As more transits are stacked and more systems are studied, the question has already evolved. It's no longer simply, is there water? It's, where can water survive? And that question is mission planning in disguise. It depends on stellar type, planetary mass, magnetic shielding, and orbital distance variables we can measure now, or soon. Every region of that parameter space we chart brings us closer to the long-term target, a truly Earth-like planet with stable, life-supporting air in control rooms and labs. Researchers are already preparing to apply these same techniques to cooler worlds around quieter stars, looking for the boundary between airless and atmospheric planets. Once that boundary is pinned down, statistical surveys can do what single discoveries cannot estimate: how many potentially habitable worlds the Milky Way might actually contain. The work continues because the reward is bigger than any one planet, understanding what it takes for a world to breathe, and whether this nearby super-Earth carries a transient veil of steam or simply reflects water from the cool scars of its star. It has already delivered something rare, a reminder of how delicate the balance is between heat and gravity, between retention and loss. Every new measurement narrows that balance, turning speculation into constraint until, eventually, the numbers stop being abstract and become knowledge. If you enjoyed this video, please consider leaving a like. It really motivates me to continue these journeys.